Hey there, here is another question from static equilibrium, which is as shown in the diagram or the figure below. A bicycle wheel is at rest against a curb. If the wheel has a radius r, mass m, and is at rest against the curb of height h is equal to 0.16 times the radius, how much force must you apply to the axle to make the wheel start to rise up over the step? So in a sense, what you want to do is you want to roll this thing up over the curb. So the question is, how much force do you have to apply on the axle? That's the axle. So you're applying this force, and how much force do you have to apply to make this go over the curb? Now that's the question. Now remember that the height of the curb is h, and because we know that this is going to be the radius as well, this gap here is going to be the radius minus h. Okay, radius minus h. Now the force is acting. The weight of the wheel acts vertically down through its center. That's mg acting vertically down. And then you have the force of the curb pushing back on this wheel, and we have no idea of how much that is. And so in order to avoid that force, which I have called Fc, the force of the curb, we're going to calculate the torque about this point. Why? Because then this force Fc does not create any torque there. So we're going to calculate the torque about this point. Okay. So d is the distance. D is that distance given there, and so this is r minus h. Like I explained before, this let's see, this whole distance is the radius. This is h, so the remaining distance must be r minus h. So really there are, with respect to this point, there are only two torques here. One is the clockwise torque set up by the force F, because it's trying to rotate it in the clockwise direction. But then you know that it would be equal to F times this distance, because we always take the perpendicular distance from the pivot, and this is the perpendicular distance from the pivot. So the clockwise torque is going to be F times this tiny distance. The counterclockwise torque is going to be mg multiplied by the perpendicular distance, which is d. So that's it. So what we need to set up is mg times d should be equal to F times r minus h. But if you look at this right angle triangle here, which I've given in dotted lines now, take a look, that small right angle triangle here, and you apply the Pythagorean theorem there, the Pythagorean theorem is going to give you r minus h whole squared plus d squared. R minus h whole squared plus d squared is the square of the hypotenuse. So r minus h whole squared plus d squared is going to be r squared. Now h is given as 0.16 times r, so substitute that, square it, plus d squared is equal to r squared. R minus 0.16 r is 0.84, and when you take the square of that, you get 0.7056 r squared, plus d squared is equal to r squared. Now rearrange the terms. Get d squared on one side, get r squared minus 0.7056 r squared. So you can take the difference between these two, get it as, and then take the square root, you get it as 0.543 r. Now take that and substitute it back into this equation to get mg times 0.543 r is equal to F times R minus 0.16 R, because H is 0.16 R. So that's 0.84 on the right side, 84 R, and the R's can get cancelled. And then when you rearrange, you get 0.543 divided by 0.84, which gives 0.646 times mg. So that is the answer.